Somewhere in a lab outside Los Angeles, a machine the size of a microwave just breathed for the first time on another planet, and almost nobody noticed. But that one quiet exhale is the reason a billionaire is now betting his entire company on turning dust into a factory. And if that sounds insane, keep watching, because insane is exactly where this story starts. Before you write this off as another billionaire fantasy sold to you in a keynote, sit with one uncomfortable fact. Nothing you're about to hear is imaginary. Every machine, every chemical reaction, every piece of hardware in this story has already run, already worked, already produced results somewhere on Earth or somewhere already in space. This isn't a pitch deck. It's an inventory of things that already exist, waiting to be stacked on top of each other in the right order, on the right ground, at the right time. And once you see the whole chain laid out, you'll understand why the people building this aren't chasing a dream, they're executing a checklist. Forget the flag-planting moon landing footage burned into your memory since childhood. Forget the postcard photos of astronauts bouncing in low gravity. What's being planned right now is not a visit. It is not a monument. It is not even a colony in the romantic sense you're picturing. It is a factory built on ground no human has ever touched, using materials and no supply ship will ever carry. And the terrifying part is that every single piece of technology required to make it real already exists on Earth today, tested, working, sitting in labs, waiting to be assembled into something that has never existed anywhere in the history of our species. So let's ask the question nobody wants to say out loud. If you stripped away every rocket, every launch pad, every headline, and left one machine standing on the surface of the moon completely alone, could it actually keep itself alive? Could it turn dust into oxygen? Could it turn dust into walls? Could it turn dust into rocket fuel? The answer, according to NASA's own published data, is yes. And that answer is what turns a fantasy into a countdown. Picture the landing first, because everything else depends on getting this part exactly right. The target isn't some flat, forgettable stretch of gray plain. It's the lunar South Pole, a place where certain crater rims catch sunlight almost constantly, while the crater floors right next to them have sat in absolute darkness for literally billions of years, cold enough to trap ice that has never once melted. That contradiction, permanent, light a few hundred meters from permanent night, is not a curiosity. It's the entire reason this location was chosen over every flatter, safer, easier spot on the moon. Sunlight means power. Darkness means water. And water, when you're building something that has to survive without resupply ships, is worth more than any mineral you could dig up. So the boots hit the ground, and before a single wall goes up, before a single machine gets bolted into place, there's a survey, because building blind on an alien world is how you kill a program before it starts. Ground-penetrating radar sweeps beneath the dust, mapping what's hiding under the surface. Ice pockets, buried rock, unstable ground that looks solid but isn't. This is the invisible blueprint the entire base will be built on top of. And get it wrong, and everything after collapses, literally. Robotic graders roll out next, flattening a stretch of regolith into something close enough to level that a lander won't tip on its next descent. And here's the detail that trips people up. Nothing moves the way it should. At 1/6 of Earth's gravity, dust doesn't settle the way it does at home. It drifts, it hangs. It behaves like it's underwater in slow motion, and every machine sent to this place had to be re-engineered around that one brutal fact. Power comes next, because without power, nothing else on this list is even possible. Solar arrays unfold across the site, angled to catch that near constant polar sunlight. But even at the pole, there are gaps, brief stretches of shadow where the sun dips just low enough to go dark. So battery banks get installed to bridge those windows, because a base that loses power, even for a few hours, in the wrong moment, is a base that fails. Then comes something almost nobody thinks about until they see it. A wall of packed regolith, a berm, rising around the landing zone before anything fragile gets built nearby. Because every future landing is going to blast that ground with rocket exhaust traveling fast. Down the ramp next, part vehicle, part workshop, part emergency shelter. The single most valuable piece of mobile equipment on the entire site, because it lets crews range out from home base without ever depending on a fixed structure. Workers stake out the footprint of the base by hand, marking exactly where every future module, every future road, every future tank is going to sit, because on a world with no landmarks, no rivers, no roads, that hand-driven grid becomes the only reference point everything else gets measured against. Core samples get drilled and pulled, confirming what the radar guessed at. Real ice, real depth, real composition, because assumptions don't hold up a habitat, verified data does. A compact fission reactor, small enough to look almost unimpressive, gets lowered into place, built specifically to keep the base alive, through the brutal 2-week lunar night when solar power simply isn't an option. And cables get buried in shallow trenches connecting every system on site into one shared grid, because isolated power sources are single points of failure, and single points of failure are how missions end in silence. A communications mast goes up last in this phase, and without it, everything happening on the surface disappears into a black box, invisible to mission control, invisible to the world. Think about what that actually means for a second. Every camera feed, every telemetry stream, every warning light on every panel in that base depends entirely on one mast standing upright in the dust. Knock it over, and the most advanced human outpost off Earth goes silent, not because anything inside it failed, but because nobody on Earth would know whether it did or didn't. That's the kind of fragile dependency that engineers lose sleep over, and it's exactly why redundancy becomes the obsession of everyone involved from this point forward. Because on a world with no repair trucks and no next-day shipping, the smallest single point of failure is the difference between a mission that becomes history and one that becomes a mystery. Site prep, done. Power, secured. Communication, live. Now the real story begins, because everything up to this point could have been done with parts shipped from Earth. What happens next cannot be. This is where the base stops depending on supply ships and starts depending on itself. Regolith harvesting begins, and here's the detail that should stop you cold. That gray dust covering every square inch of the lunar surface is not waste. It is the entire construction industry of this future base rolled into one substance. There are no quarries here, no concrete trucks, no cement plants, just dust sieved into different grades, fine powder set aside for 3D printing, coarser granules saved for shielding and structural aggregate, and mixed into that dust is something almost nobody expects, usable metal, pulled out through magnetic separation because lunar regolith is quietly rich in iron. Then comes the part that sounds like science fiction until you realize it's just physics. Solar concentrators, essentially. Precision mirrors focus raw sunlight onto piles of that gray dust until it hits temperatures past 1500 degrees. And at that heat, lunar dust stops being dust and starts being liquid glass. No furnace fuel required, no fuel shipped from Earth. Just mirrors, sunlight, and time. That molten material gets poured into molds and cools into solid basalt glass blocks, strong enough to build with, and entirely free once the equipment to make it exists. And every batch of this material gets tested to failure before it's trusted with a human life, blasted with simulated cosmic radiation, cycled hundreds of times between blistering sunlight and freezing shadow, dropped into vacuum chambers to see if it cracks or holds. It holds. That's not a marketing line, that's the slow, unglamorous grind of real aerospace engineering, the kind of testing nobody puts in a trailer because it isn't exciting to watch, but it's exactly the kind of testing that separates a viable building material from a pretty rendering that would kill the first crew that trusted it. But the same molten regolith holds a second secret inside it. Oxygen, trapped in lunar rock for roughly 4.5 billion years, released the instant that material gets electrolyzed. And that oxygen doesn't just sit there as a curiosity. It fills storage tanks that will eventually supply breathable air for crew and oxidizer for rocket engines, both from the exact same batch of dust under someone's boots. Fine regolith gets blended with a polymer binder into a thick paste, loaded into feed cartridges, and that paste becomes the raw material for the next machine in line. Because every one of these steps exists purely to feed what comes after it, and what comes after it is the printer. A gantry frame, wide enough to span an entire habitat footprint, rolls into position and begins laying down the first circular wall base, centimeter. By centimeter, patient in a way no human construction crew could ever afford to be. Sensors trail behind every pass, checking for voids, checking for weak bonding, because a hidden flaw in a pressurized structure on an airless world isn't a repair job, it's a catastrophe. Layer stacks on layer and the wall climbs. A dome cap gets printed separately and lifted into position, sealed by hand along the seam, and only after the entire shell is structurally complete do. Workers cut the airlock openings because cutting first and hoping the structure holds later is exactly backwards. Solid first, opening second, always. That airlock door gets bolted in and immediately pressure tested, because a leak at this stage doesn't just fail one module, it can take the whole habitat down with it. Interior sealant gets sprayed across every surface, since printed regolith, for all its strength, is naturally porous, and this coating is what actually makes the difference between a structure and a tomb. Life support ducting threads through channels built directly into the printed walls, because air has to reach every corner, or it isn't life support, it's decoration. And then, over the entire dome, workers stack bags of loose regolith roughly a meter thick, because that single meter of ordinary lunar dust is enough to block cosmic radiation completely. No exotic shielding required, just mass in exactly the right place. A second module goes up, then a third. Tunnels connect them, and suddenly this isn't a lone habitat sitting in isolation. It's a cluster, a base, a place where a person can move from workshop to bedroom to greenhouse without ever putting a suit back on. And the printer, without pausing, moves straight to the next foundation, because a base that stops growing is a base that stops working. Compare that, for a moment, to how humans have built outposts in hostile places on our own planet. Antarctic research stations, some of the harshest inhabited places on Earth, still depend on ships and cargo planes bringing in nearly everything they need to survive: fuel, food, spare parts, all shipped across oceans on a strict seasonal schedule. This base has none of that luxury. There is no cargo plane. There is no next window before the ice melts. Every gram of material either comes from the ground beneath the machine's own feet, or it doesn't come at all. And that single constraint is what separates a research outpost from a self-sustaining settlement. Because a settlement, by definition, has to be able to keep building even if every ship from Earth stopped launching tomorrow. Power demand climbs with every new module, so the solar field expands, and a second fission reactor gets installed purely for redundancy. Because if one unit fails and there's no backup, the entire base goes dark with it. A new foundation gets poured in glass block, and this one has a very specific purpose: making rocket fuel. In a permanently shadowed crater nearby, heated augers bore down into the ice deposits confirmed months earlier, vaporizing water that gets captured and condensed, then split by electrolysis into hydrogen and oxygen, both stored separately, both essential, both, and this is worth sitting with, coming from ice that has not seen sunlight in longer than humans have existed as a species. Cryogenic tanks chill those gases down to liquid form, denser, more stable, ready for use, and somewhere in that process, a simple, staggering fact becomes real. The oxygen filling those tanks never came from Earth. It came from frozen darkness older than complex life itself. Iron-rich regolith gets smelted into metal ingots, the very first metal ever manufactured off the surface of our planet, rolled into sheet metal for tools and structural parts, and a machine shop gets installed inside one of the domes, lathes and mills for now, still shipped from Earth, but running on lunar power, cutting lunar metal, functioning as an actual working machine shop on another world, not a metaphor, not a rendering, an actual lathe-cutting actual metal right now. Pause on the significance of that image for a moment, because it's easy to let it slide past. It's just another shot in a sequence. Every previous era of exploration, every ship that crossed an ocean, every wagon that crossed a continent, still depended on tools forged somewhere else and carried along for the ride. This is the first time in the entire history of our species that a tool has been manufactured, from raw material to finished part, entirely off the surface of the planet where humans evolved. Not shipped, not carried, made. That single distinction is the quiet hinge this whole story turns on, because a species that can manufacture its own tools somewhere else is no longer just visiting that somewhere else. It's beginning, slowly, to belong there. A metal printer comes online next, producing bolts and brackets and precision parts straight from that lunar smelted stock. And a solar panel production line starts up shortly after, because lunar regolith contains silicon, and a base that can manufacture its own power. Hardware is a base that has stopped merely surviving and started reproducing its own infrastructure. That is the moment this stops being a habitat and becomes something else entirely. Fuel, metal, parts, and power, all pulled from ground that, months earlier, was nothing but gray dust under nobody's feet. A larger dome. Rises next, engineered wider than the others, because this one has to hold something none of the previous domes did: life. Hydroponic racks get installed, LED grow lights wired in, and the first seedlings go into the trays: lettuce, potatoes, the same crops NASA has already proven can grow off Earth aboard the space station, except this time under extra shielding, because plants, it turns out, are more sensitive to radiation than the crew growing them. Tunnels now stitch every zone together: habitat, greenhouse, workshop, fuel plant, one continuous pressurized environment. A paved road connects the base to the landing pad, because unpaved dust kicked up by every rover pass slowly grinds equipment to failure. And a taller blast wall rises at the pad itself, because the next landing is coming, and nobody wants their finished base sandblasted by it. Then comes the moment every single step before it was building toward: a full systems check, power, air, water, fuel, tested together for the first time as one integrated whole, and a spacecraft sets down on the pad and refuels, using oxygen made entirely from lunar material. Read that back slowly. The first off-world refueling in human history, using fuel that never touched a launch pad on Earth. Every rocket engineer who has ever worked on this problem will tell you the same thing. Propellant is the single heaviest, most expensive, most limiting factor in every deep space mission ever flown. You can build the most brilliant spacecraft in history, and it still goes nowhere if you can't carry enough fuel to get it home. That's the equation that has strangled every serious Mars proposal for the last 60 years. Because the fuel needed for a return trip weighs more than the ship itself, more than the crew, more than everything else combined. The moment a tank fills with oxygen that was never launched from Earth, that equation breaks, and it breaks in humanity's favor for the first time ever. A full exterior inspection follows. Every seal, every panel, every shielding bag checked by hand, and a permanent navigation beacon goes up, guiding every future landing precisely home. The lunar base stands complete, built from dust, ice, and sunlight, with nothing shipped from Earth except the printer that started it all. And then, almost anticlimactically, the refueled ship lifts off again, not heading home, heading further out, because the moon was never actually the destination, it was rehearsal. Mars is the exam. The landing site this time is Arcadia Planitia, chosen for exactly one reason: subsurface ice sitting close enough to the surface to reach without absurd drilling depth. The same survey sequence runs again: ground radar, core samples, site staking, except now there's something the moon never had: an atmosphere, thin but real. And that thin atmosphere changes everything about how machinery behaves, how dust moves, how heat escapes, how sound even carries. It also changes something the engineers didn't fully appreciate until they modeled it properly: wind. Not the violent ship-flipping storms of old science fiction, but thin, persistent, gritty wind that constantly reshapes dunes, buries equipment left in the open, and slowly sandpapers exposed surfaces over months and years. It's a quieter danger than a Hollywood dust storm, but a more relentless one. The kind of threat that doesn't destroy a base in one dramatic night. It wears it down one grain at a time, which is exactly why every design choice on Mars accounts for decades of exposure, not just the first landing. Solar panels go up again, angled differently this time, because Mars's dustier sky lets through noticeably less direct sunlight than the moon ever blocked, and a bigger reactor array gets installed alongside them because Martian dust storms can smother the sky for weeks at a stretch. And a base without serious backup power during a storm like that is a base gambling with its own survival. A protective berm rises around the site again, and a heavier, more rugged pressurized rover rolls out, built with bigger wheels for softer Martian ground. Because a machine engineered for the moon and dropped onto Mars unmodified is a machine engineered to fail. The drill goes down and hits ice, solid, confirmed, and that single moment quietly becomes the linchpin the entire Martian plan was built around. Because without confirmed ice at this exact spot, nothing that follows happens. An atmospheric processor powers up, pulling in Martian air, which is roughly 95% carbon dioxide. Not a waste gas here, but a feedstock, the raw ingredient for what comes next. Cables get buried between every system exactly as they were on the moon, because a method proven once under brutal conditions doesn't need to be reinvented, it needs to be repeated. A comms mast rises, aligned back toward Earth, and here's a detail worth pausing on. At this distance, a single message takes somewhere between 4 and 24 minutes just to arrive, meaning nobody on Mars is having a real-time conversation with mission control, ever. Every decision on the ground has to be made locally, immediately, without waiting for permission from a planet that's currently 20 minutes away by radio. That delay quietly rewrites the entire relationship between the crew and the people back home. On the space station, a problem can be talked through in real time. An expert on the ground can walk an astronaut through a fix, sentence by sentence, back and forth, in seconds. Here, that back and forth simply doesn't exist. A question sent the moment something goes wrong won't get an answer until nearly Radiation defense. A greenhouse dome rises again, bigger than its lunar counterpart because Mars's dusty sky lets through even less usable sunlight. Hydroponic racks and LED lights installed exactly as before, adapted for a colder interior climate. It's easy to focus purely on machines in a story like this, reactors, printers, tanks, and forget that at the center of every one of these decisions is a human being who has to actually live inside what gets built. A crew member walking into that greenhouse isn't just checking on a science experiment. They're standing in the one room on the entire planet that smells like soil and green leaves instead of metal and recycled air. And engineers who have studied long-duration isolation missions will tell you that psychological detail matters just as much as the calories the plants produce. Because a mind that never sees anything living, anything growing, anything that isn't gray dust and gray walls, starts to fray in ways no amount of physical safety can fix. A smelter goes up. That brick from the very beginning of this story, the one sitting quietly in someone's hand, is the same material holding up every dome across both worlds. A small oxygen-making experiment that once produced breathable air by the gram, tested and proven on Mars years earlier, scaled up until the exact same chemistry fills the tanks of a spacecraft big enough to carry humans home. And maybe that's the detail that should actually keep you up tonight. Not the size of the domes, not the number of tons of propellant, but the fact that none of this required a single technology that doesn't already exist on Earth right now, today, in a lab, in a test facility, in someone's hand. The only thing missing is the decision to put all the pieces in the same place at the same time. Nothing here needed to be invented. It only needed to be assembled in order on ground that's been waiting billions of years for someone to finally show up. Think about how strange that really is. For most of human history, every great leap forward required a breakthrough nobody had seen before. Fire nobody had tamed, an engine nobody had built, a vaccine nobody had discovered. This leap is different. This one doesn't need a miracle. It needs logistics. It needs sequencing. It needs someone willing to spend the money and take the risk of putting a printer, a reactor, and a rover on a rocket and letting them prove, on real alien ground, what a laboratory on Earth could only simulate. Every skeptic who says this is decades away is right about the difficulty and wrong about the ceiling, because difficulty is not the same thing as impossibility. And every single piece of this puzzle has already crossed that line from theory into working hardware. The oxygen has already been made. The bricks have already been printed. The methane has already burned in a real engine. What hasn't happened yet is simply all of it, together, at scale, on the same patch of ground. And history has shown again and again that the gap between proven pieces and a finished system is measured not in miracles, but in years, funding, and stubborn persistence. So the next time someone shows you a rendering of a dome on Mars and rolls their eyes at how far-fetched it looks, remind them of the brick. Remind them it was real. Remind them that dust this whole time was never the obstacle. It was always the raw material, just waiting for someone crazy enough or patient enough to finally put it to use. And maybe that's really what separates this story from every other space fantasy you've scrolled past this year. It doesn't ask you to believe in magic. It doesn't ask you to imagine some undiscovered element or some engine physics hasn't explained yet. It only asks you to imagine patience, applied at a scale most people never have the discipline to sustain. One printer, one reactor, one tank at a time, on ground that has been sitting there, silent and unclaimed since before there was anyone around to want it.